So that's enough of the intros and all that kind of stuff and what we've got coming up. I'm now going to hand over to our two speakers tonight. Obviously, first speaker is going to be Tim Kadlec. Secondly, it's going to be Ilya Grigoric. And basically, let's get this show on the road. So up you come, Tim.
My computer is desperately trying to get me to connect to the M&S Wi-Fi, apparently. Here we go.
There you go.
All right. All right, so how many people here have children? Anybody raise them? Yeah? Okay. How many people have more than one children? This is going to be great, guys. Good. How many people have ever tried to get those children to stand next to each other, looking at a camera, with smiles on their faces for one beautiful picture where nobody's blinking or anything? Has anybody ever tried to do that? It's impossible, right? Like, I've got 4 children, and we've decided that this is just something we cannot do. We've accepted that we will always fail at taking the family photo. My parents, I was one of 5 children. My parents never came to that level of recognition. They insisted on trying to find the perfect photo. My dad was obsessed with photography and would carry this like a gigantic bag, and he'd be walking around on all of our trips like this, which couldn't possibly be healthy. And he also carried a tripod with him. Yeah, that was the kind of vacations we went on. And he would bust out the tripod and he would set us all up and he would try to get us all to take a photo. And it never worked, because what happens is, at first, it's innocent enough, right? Somebody sneezes, or somebody blinks at the wrong time, or somebody gets distracted by something going on. But then before you know it, people are getting upset because somebody is touching somebody's arm and somebody's looking at somebody the wrong way. And then people are getting very upset. They're starting to cry. They're asking, when can it be over? And that's just the parents. That's not even what the kids are doing. But my dad never came to the realization that he would never be able to get this perfect photo. But the outcome was that we had shelves and shelves and shelves of photo albums. I've yet to ever meet anybody with as many photo albums on their shelves as we had. And while we never went like full film projector mode on anybody who came over, we did bust out the photo albums fairly often and make people look at them and look at all the vacations we went on and the 30 different shots from when we were at that one spot in the zoo. And to be fair, though, there's something kind of cool about that, right? There's something kind of cool about looking back at all those old images and seeing these memories of places that you've been that maybe you forgot about a little bit, and seeing those memories start to flood back. It's usually cool until you find out that there's photographic evidence of you in a fanny pack. Then sometimes it's not so great and you wish they could disappear. But we're taking a lot of photos now, even more so. Like now, when my dad did it, I thought it was absurd. But now when you consider how many photos everybody takes today, it was nothing. Thanks to the advent of the mobile phone, we walk around with cameras inside of our pockets. So all of us become amateur photographers. And we catalog every moment of our lives from every possible angle. And I do mean every possible angle. This is a real product. Not an SNL product. This is a real thing called the Belfie stick. It is for taking photos of your bum. That's how we say it over here, right? Yes. So apparently, I just want to stop on this for a second. We live in a society where it's so important that we get good photographs of our backside that we had to construct a special device to help us do it. I mean, when I was a kid, we had to use photocopiers for this kind of thing. Like, this is pretty... It's amazing, technology and how it advances. But we take a lot of photos. In 2012, up to that point, in the year 2012, we took 10% of the photos ever taken in that one single year. That means, like, modern photography, as we know it, was about 1839 or so was the first photograph. So in 172 years, we took about 90% of all the photos. And in one single year, we added another 10%. That's ridiculous. In 2015, we uploaded 1.8 billion photos per day to sites like Facebook and Instagram and Twitter and Snapchat and all these other floods of things. If you look at data on what are the most popular social networks for the younger generation now, it's not things like, it's all these different photograph things. It's Instagram, it's Facebook, it's all the places where they can store these memories digitally. That's what matters to them today. And then we turn around and we use these photos a lot on our sites. This is the Facebook Instant Articles page, but it's a very common design tactic right now, right? Have this huge image that you display. On the desktop, it's usually, full width, big banner hero image. On the mobile device, it's not uncommon to see things like this. But there are serious consequences to using all of these images on our site. So again, on this particular page, this is from my Moto X. And this image is actually occupying a space of 360 pixels by 510 pixels. That's the visible space that that image is filling up. Now, the image that's actually being passed down is much larger. It's actually 1,300 pixels by 1024. Not entirely picking on the Facebook Instant Articles page, because this is a very common thing that we see. It's, you don't have to look very hard to find this happening. But this is very expensive because the browser has a lot of work to do to get this image onto the screen. We're fairly familiar by now with the idea of having to request the image and download it over the, transfer it over the wire. But then the browser needs to decode that into some sort of usable data. It needs to copy that over to the GPU, and then it needs to display that onto your screen. And each of these steps has their own little complexities, and each of these steps can have some serious implications on perceived and rendering performance. What I want to focus on today primarily is this decode and after step, because the request step, I think, again, that we've fairly got that established. If anybody still has questions around that, I'm happy to talk about that afterwards. But I want to focus on what happens after the browser has the image. Primarily, we're going to talk about JPEGs because despite the fact that WebP and all these other different formats are coming out with some really great file size savings, JPEG still dominates the internet. You're still looking at nearly 50% of the images online are JPEG format. But also because JPEG has some of the most interesting things happening from a browser perspective in terms of optimizing this process of decoding and displaying. So when you use an application like Photoshop or something to create a JPEG image, what it has to do is it has to take this original RGB data, it has to convert that to YUV, it has to apply some chroma subsampling, it goes through DCT quantization process, some Huffman encoding, and it finally spits out this actual bitmap file, the file that you save to your disk. This is the process of encoding the image. So what the browser needs is the browser needs to actually reverse all of this and walk backwards through it, basically decoding this back to some sort of RGB data that it can actually display on the screen so it knows what to print out. So this decoding process, you can see the cost of it in a few browsers, not all. Chrome does a really good job of it. If you look at Chrome, you can get, you would do a timeline recording. You can filter it down by decode, and you'll see the actual time spent decoding these images. They do break it up, so it's calls to the decoder. It's not like the one image is not all bulked together in timing. So what you see here is like 26 milliseconds being spent on that image. In actuality, it's about 58 milliseconds in total. It's just showing up in different spots within the timeline. But so you can get at it through Chrome. You can do Chrome tracing, which actually is this kind of intense little power tool. Has anybody done any Chrome tracing stuff? Yeah? I'm going to be, Ilya, have you done any? No? Okay, I didn't think so. I'll be honest, it's kind of intimidating. It is. Like, I still sometimes, my eyes gloss over looking at it. But it's also incredibly powerful. There's so much data here. But if you do a trace and load the page in the background and record the trace and then analyze it, you get this scary looking chart. And when you drill down into this, you can get detailed information about exact steps that the browser is going through to go through the decoding. So here we've got it filtered by decode and scale, and we're focusing on that particular measurement to see how long the browser is spending on the CPU doing the decoding and scaling it to the appropriate size. Canary actually has a simplified version of this right inside of the timeline recording, which I think is actually really nice, and I hope that this is not something that's just a Canary thing. I hope this makes it to Chrome, because this makes it much easier to digest, I think. You don't have to go through the whole Chrome tracing process. It's just there inside of the timeline. And like I said, it's simplified, so there's not quite as much noise. It's reduced to the stuff that you're probably more typically going to need to be using if you're actually doing this sort of analysis. Edge actually does a really good job of this too. Edge, you can see this is from Surface Pro. A little expensive here, about 295 milliseconds decoding that big image, although this is on desktop, so it's now 2,800 pixels wide. It's a huge beastie thing. But Edge provides pretty good tooling on this as well, so you can dig into that. Nothing quite as intense as the Chrome tracing stuff yet, unless you use the Windows Performance Analyzer, which is a separate tool. You can get that kind of granular detail from that. But again, we're focusing primarily on the browser tooling right now. So using this, what I wanted to do is I wanted to find out how much time does the browser actually spend decoding these images? How expensive is this? So I made this exquisitely designed page. It took 5 hours laying it out and everything. What I did is I just grabbed 10 images. I have a button where I can keep continually adding more so I can see how it exaggerates when you have 20, 30, 40, 50 images on a page. And I have 3 versions of the page. I have one version where it is the original sized image, so as I grabbed it from the source, which is something like 1,200 pixel wide. I have another version of the page where it's double sized, so I'm serving a 400 pixel wide image despite displaying the image at 200 pixels. And I have one version of the page where I've got them appropriately sized. So I've got them all resized to 200 pixels exactly as they're going to display in the browser, so the browser doesn't need to worry about scaling. And I loaded this up and recorded probably about 20, 30 test runs, and then figured out what we were looking at here. Apologies to Ilya. I did this research before his post talking about how medians are terrible. So I'm going to use medians here. Don't judge me. But this is what we came out to. Basically, the median for resize. So if I have a 200 pixel image, I've sized it appropriately. It didn't take very long at all. Like, it was a very quick process decoding. There wasn't much time spent on the CPU. If we did it double, so if we had a 400 pixel image that we now tried to send to the browser, and the browser had to decode and then scale it down, we got about 26 milliseconds. And if we did the original size, so about 6 times the actual dimensions, so from 200 pixel wide image to a 1200 pixel wide image, we had a very, very large jump in time spent on the CPU decoding. For percentages, because that can be easier to kind of understand, double was about a 235% increase, and large was a 3,291% increase. So when we send large images, we are really making the machine work hard. And I want to clarify, these are tested on on this MacBook Air, which is like a 2014, 2015, 13-inch MacBook Air. It's not like, it's not a bad device. It's pretty powerful. It's all right. It's better than most of your users are probably going to be using. So I wanted to get a more real-world perspective, so I also tested on a Nexus 4. Now, the Nexus 4 is like, it's not the top-of-the-line phone, right? It's not the thing that we would go out and buy, but it's going to be a little bit more indicative of what our typical user is going to be doing, because they're going to probably be lagging a generation or two behind in terms of hardware. That's far more typical. Well, I tend to upgrade as soon as I can, every couple months. That's not what my neighbor down the street's going to be doing. And even with that, this isn't a bad device. This is, 2 gigs of RAM, quad-core CPU. It's not a bad device at all. It's still pretty powerful in the grand scheme of things. On this device, when it's resized, so it's appropriately sized, we still spend about 30 milliseconds on the CPU just decoding to display these things. As soon as it's double, that jumps up to 100 plus milliseconds. Remember, this is just for 10 images. And as soon as it's large, that's 6 times the size, we jumped up to 1.5 seconds, an absurd amount of time on the CPU trying to process this and decode this all into some sort of usable data. Percentage-wise, that's almost a 5,000% increase, which is a scary big number. So it's at this point when I was researching this stuff that I started to go through, I started to hyperventilate a little bit, because these are big numbers. Where I come from, 5,000% is a lot of percents. We have trouble counting that high. So the first thing, and this should be hammered into everybody's head by now probably from every other discussion you've ever heard related to images, but the very first most important thing you can do is make sure that you resize those images. And I really like to stress just how important this is. And I've given this talk once before, and when I did, I talked about, I threatened cats, because I don't really like cats, and people in the tech community like cats. I said I would hurt a kitten, if the images weren't resized, and people were all up in arms. It worked great. However, there's still a lot of large images out there, and so I'm afraid I'm going to have to get really nasty today. And I know how proud people are here of their mastery of the English language. And I know how you feel about what we Americans do to it. So here's the deal, and I'm really sorry to have to get this bad. But if we're not going to resize images, I'm going to do things like say huger, which I've already done this week, so don't tell me it's happened. I'm going to do things like repeatedly point out that you can't possibly pronounce router as router, because it's not spelled like this. It is a router. There's no double O there. And perhaps worst of all, and this is the one that I'm afraid I might get kicked out for, I will purposely leave the U off of color. I'll do it. So if you guys don't want me to kill your language, this is what you should be doing. Resize the images for sure. So now I want to talk about like this process. So after it's got decoded to the RGB data, and it has to transfer this over to the GPU so it can actually display this on the screen. Now, because the decoding process is expensive, what it does is it actually stores that decoded data inside of the memory. So there's memory impacts here of these images as well. So let's go back to our Facebook Instant Articles image here. What happens, what the browser needs is on a pixel by pixel basis, the browser needs to know the RGBA value for each individual pixel so that it knows what to paint in that pixel on the screen. This means that that decoded image has a really big memory size, big memory footprint. The formula, the basic formula is the width of the image times the height of the image times 4 RGBA. So we've got this 1300 by 1024 pixel image that's being sent down to a mobile device. And we apply our little formula and do a little bit of math, and we end up spending about 5.1 megabytes in terms of memory for that decoded data. Just one single image being decoded. You can get at the decoded data inside of a couple browsers. So if you go to Firefox has the about memory, which actually does a really nice job of breaking down the memory used for each individual resource. You can get to the images, you can get to different HTML elements, JavaScript heaps. It's all profiled pretty nicely here. Edge also has really good tooling around memory. You can drill in here, and you've got you can see these HTML div elements. These are the ones with like the background images applied, and you're seeing they're taking 15 and 11, 12 megabytes of memory there. I haven't been able to get this sort of detailed information on an image-by-image basis from Firefox or Chrome at the moment. But Firefox does. Sorry, Safari and Chrome at the moment. But Firefox and Edge do a good job of it. So if we had resized this to the exact size that it was going to be displayed at, instead of sending down that 1300 by 1024, and we apply our formula, it would have only been about 734,000 bytes, which means that just by resizing to the appropriate size, we would have saved about 4.4 megabytes in terms of memory on that device. Now, this is a big deal because while I'm talking about the Nexus 4 having 2 gigs, at the last Google I/O, Jen Fitzpatrick, who was a VP of product management for Google Maps, said that 25% of new Android phones are shipping with 512 megs of RAM or potentially less. So when you talk about a single image taking as much as 5 to 6 megabytes, and consider some of the sites that we've seen where we've got these massive galleries of these high-resolution images, and then consider that the phone also needs to use that memory for other things besides the browser. Apparently there's native applications, I hear, are a thing. It starts to really add up, and it starts to really add up quick. And I want to say that this extends a little bit just beyond the resizing. If you're also doing like spriting, like this was a sprite used on the LinkedIn site, and consider all the white space, which is there for like convenience in terms of spacing and things like that. But all that white space adds up because we end up with about 987K of decoded data or decoded data being stored in memory. But if you were to eliminate the memory, the white space, and have this much more condensed, you'd probably shave that probably by about 33, 40%, somewhere in there. So it has implications beyond just the resizing images. But again, I'm very serious about this, so remember. Interesting thing about the resizing images and the data decoding thing is it has interesting implications on where you should focus your efforts first. So if you have a 600 by 600 pixel image, and you have a 200 by 200 pixel image, and let's say that you you're building a responsive site, you've got different breakpoints for these images where you're going to serve up a different size. Let's say you decided to do it evenly. So maybe every 50 pixels you serve a different size. So you do 550 pixels, 150 pixels. You serve this same size image, and you just have it shrink down by about 50 pixels inside of the browser. That's it. It sounds pretty innocent. For the larger image, you're wasting 230,000 bytes. For that little image, you're only wasting 70,000 bytes. So if you have this even breakpoint in terms of the size of those images, the memory implications of those larger images is much more exaggerated than the smaller images. So if you're doing a responsive image breakpoint thing, you might want to consider staggering it a little bit closer together as you get to these larger image sizes. So on the smaller image, you can get away with letting it stretch a little bit further from a memory footprint perspective. And on the larger the image gets, you might want to start bringing those breakpoints in closer and closer and closer to eliminate the memory overhead. So that was one interesting sort of takeaway from some of that investigation. So far we've touched on how it's not just the data or the size of the stuff on the wire, but you've got memory impact, you've got battery impact, because all this decoding and this passing back and forth between the CPU and GPU is expensive. That's why if you look at a site that is very image intensive, maybe like a Pinterest or some sort of gallery-based thing, and you keep scrolling and scrolling on those darn infinite scroll things, and you feel the phone burning up, that's what's happening. It's not great for the life of device, as it turns out that when your phone gets hot enough to burn your hand, it's also bad for the phone. And then, of course, there's all the CPU and GPU overhead. So all of these things and all of these different considerations, as a developer, it's very tempting to put my foot down and say, you know what, this is what we need to get back to. Let's go back to the roots. And the designers throw me out of the room at that point. So we have to be willing to compromise. Thankfully, the browsers are coming to our rescue in certain ways on some of these things. They've gotten very intelligent, particularly around JPEGs, with how they're handling this from a memory perspective. So remember this process, the decoding process here. And it has to go through the decoding, the dequantization, the upsampling, and then finally convert it to the RGB data. So the Internet Explorer team, when they were Internet Explorer, decided, what if we split this up a little bit? What if we put the GPU and put that in charge of part of this process, the chroma upsampling and the conversion to RGB data? So to understand the impact of this and why this is an intelligent move that they made, we need to look a little bit at the chroma subsampling sort of process. So the way we view images, we view light, luma, and we view chroma, color. We're far more susceptible to changes in the light than we are to the color. So as long as the light is high resolution and very detailed, we're going to pick up those details, and we can cheat a little bit on some of the chroma stuff. That's sort of the whole idea behind chroma subsampling. So in the YUV or YCB-CR, which I guess is more appropriate for digital, but in that color space, it breaks it out into your luma channel and two chroma channels. There's the CB, which is the diff of blue, and the CR, which is diff of red. And the whole idea behind chroma subsampling is that you can start to optimize by compressing those chroma channels a little bit more intensively. So let's dive into this. And this is, apologies if you get headaches. Subsampling it's kind of a tough, it's been around forever. It really has. It's not something new to browsers or to the web or anything like that. But it's kind of a difficult thing to wrap your head around. At least it was for me, but I could just be slow. It's possible. Typically, chroma subsampling follows a JAB notation. So the J is the width of the section of the image being analyzed for compression. A is the number of samples in the first row of that section. And B is the number of different samples that you take from the second row of that section. So let's walk through a few examples, because that might be clear as mud at this point. So let's say that we have this image. I've made them purposely very differently colored so that we can see the impact in terms of degradation here, and to sort of exaggerate that a bit. Basically, every chroma subsampling that I've ever seen on the web, it starts with the 4. It's analyzing areas of 4 pixels wide. It's the A and the B that vary. So we're going to look at this particular image, which conveniently is 4 pixels wide and 2 pixels high. It's just the perfect size for analyzing. So from a light perspective, again, we want as much detail as possible. So what we're going to do with the luma perspective is we are going to take a sample on each individual pixel all the way across. So our luma channel ends up looking like this. We have a large amount of detail inside of the luma channel. And now we're going to start to look at how we can optimize some of the color stuff. So 444 is a very common variant. In fact, the most common, as we'll see, which actually means there's no subsampling happen. It's very sad. What 444 says is we're going to take, on the chroma channels, we're going to take 4 samples in the first row, and then we're going to take 4 more samples out of the second row. So we are sampling 4 times across and 4 times across again. So we've got 8 data points for these 8 pixels. So our chroma channels look like this. There's no degradation. They're very bright and beautiful. And we combine them with our luma, and we end up with the exact same image that we had. There's no perceptual difference at all. If we break this down, let's look at 422. So in 422, what we're saying is, again, we're going to take a 4-pixel wide area. We're going to take 2 samples from the first row. So we're going to skip over every other here. And we're going to take 2 samples from the next row, again, skipping over every other. So we get about a 50% savings here already in how many samples we've been taking in the data. This means that this turns into this. We get a little bit of degradation in terms of the chroma, in terms of the quality. So when you apply the Luma channel, you end up with a little bit different image than what you started with. 411, same sort of thing. 4 pixels wide. We're going to take 1 sample from the first row, and we're going to take 1 sample from the second row. Now, at this point, we're starting to see some really heavy savings. We've got about 75% savings in terms of how much data is being taken on these chroma channels. But the degradation is extreme, right? Because we've only sampled 1 time on each row. So we're starting to see more and more quality loss. So when we apply our Luma channel, we have something that is very different than our original image. And finally, 420, which is the second most common version of subsampling used on the web today. A little more complicated just in terms of thought process because that 0 is new. But it's not too bad. Again, 4 wide, 2 samples from the first row. The 0 says we're not going to take any samples from that second row. We're just going to extend that first row down. So again, we've only taken 2 samples here. We've got a 75% savings. We've got extreme degradation in terms of the color quality, and we have an image that looks a little different than what we started with. Now again, I've exaggerated all of these to make it hopefully a little clearer, like what's happening in terms of how it's picking those chroma values up. In reality, it's not going to be that noticeable depending on the image. This is a more real-world example where you've got the Luma and the chroma channels separated by 422, 420, and you can see that it's a little harder to tell, right? I mean, granted, I've got this on a projector, so I'm cheating, but whatever. It's not always going to be as obvious and as bad as the degradation as the exaggerated version. So if we look at this, what Internet Explorer decided to come up with was this idea of what if we split this out? So what if we decoded the data, or we decoded it, and we copied over to GPU, and then we applied the chroma upsampling and the final conversion to RGB on the GPU. So this decoded data that's now stored in memory is just stored in the YUV color space. So we're not having to store as much data. It's not as heavy from a memory footprint perspective. So our formula, which was width times height times 4, the RGBA, becomes a little bit more complicated. Width times height times 3, and then you have to take in and factor in the subsampling level, like we were looking at the 75% savings for 420, the 50% savings for 422, things like that. So it's a little bit more complicated. This is mostly there for the people who really like doing math by hand, if you're really into that. But what that happens with this image is originally, without this GPU decoding process, we had that 5.1 megabyte memory footprint. But you can see with chroma subsampling applied and with that YUV data being stored, we're getting significant savings in terms of memory. In fact, 420 works out to be about a 62.5% memory savings, which is a very big deal, especially if you have a site with lots of gallery images or big hero images all over the place. So ideally, this would be very widespread on the web. I would love to see this being used more often, this 420, so that browsers can take advantage of this. My colleague, Colin Bendel, for those of you who don't know him, this is Colin. For those of you who do know him, I will be making this image available after the presentation so that you can share it. He did a bunch of research where he looked at 1 million images off of the Akamai network and looked at all the subsampling levels being applied. And what he found was that 60% or so of the images, of these 1 million images, they were 444. So there was virtually no savings going on at all. And only 39% applied 420. There was a 0.9%, which is all sorts of random things, like the things we talked about, as well as some 3x2 by some really weird things from like Paint Shop Pro that should not exist anymore, but somehow do. I don't know. But I'd love to see this number go up, like this 420, because it's got a big memory impact. So ideally, we'd be doing more of that. That means primarily just watching how you're saving your image out of Photoshop, out of whatever your favorite photo editor is, or running it through some sort of a process. You can convert this through Image Magic, any sort of command line thing that you want to do. You can automate this. It doesn't have to be something that you manually remember to do or you make your designers do. There's ways to get around that. This also comes into play because browsers have another feature called image pooling. So this is a trace off of Chrome. This is a popular news site, which I thought was going to be nameless, but like 3 screens later, it actually has the name of the news site in the image name. So just don't pay attention to that. What happens is I'm scrolling down. There's this big pause here, which is where I paused to exaggerate that I had reached the bottom of the page, and then I started scrolling back up. But if you look at it in detail, what's happening here is you'll see that this image, this Pope climate change image from towards the top of the page, actually shows up again as we start to scroll back up. Because what happened is that there's so many images being used. In fact, there's over 26 megabytes, around 26 to 30 megabytes it was or so, being stored in memory, that the browser has to start offering some of this back to the operating system, because the operating system might need this memory for other things that it's doing. So it basically works like this. The browser is using up all of this memory. It checks in with the operating system and it says, hey, you know what, do you need any memory? And the operating system says, yeah, I'll take some of that because I've got some things going on. Now, whenever this happens, it reclaims that memory space back. And now the browser has to go through the decoding process once again to get that image back in. So the next time it goes back up, it goes through the entire decoding process, copying over to the GPU. All of that stuff has to happen once more because it's given up that memory space that it had. So when we can give a 62.5% memory savings, that actually can have a significant impact on this as well, which is great for battery life, which is great for reducing that CPU overhead. So basically what happens is now we've got it split so that the Huffman decoding and the dequantization happen on the CPU. The data is stored in YUV format, and then the GPU takes care of the rest. Edge does this. Microsoft 11 led the charge. Chrome, Blink, Opera, they do this as well. Edge does it like everywhere. And Chrome has some criteria that they're factoring in, which is actually pretty intelligent. It's smart. It's a good choice. But this has a significant impact on the display. So remember this page that we had tested and where we're spending about 1,500 milliseconds on the CPU. So let's see if we can enable this GPU decoding on this inside of Chrome. So last I looked, Chrome decides to enable it if there is not multiple rasterization threads, it's Android 4.4 and up, or it's a Nexus device. And most important, you've got your little viewport tag inside of there. Sound about right? If that's all there, it's going to enable the GPU decoding process. It also looks nicer. Hey, yay for responsive design. But it has a significant impact now on reducing the cost on the CPU for this decoding process. So we go from the original resized images spending about 30 milliseconds on the CPU down to 5. We go from the double size, spending 102 milliseconds, down to 27. And for the ridiculously large ones that we were passing down, it cuts that down to about 460 milliseconds. So still not light, but we're talking about a really hefty decrease in how much time is spent on the CPU decoding these images, thanks to that GPU decoding. And so all that instant articles, it's not a hard thing to enable. All they would have had to do, if you look at their viewport tag, this is what it was. All they would have had to do is add that width, device width to this, and boom, they would have had that sitting there. And ideally, they would have killed the maximum scale as well, because that's just, don't do that. It's bad for accessibility. But that's beside the point. So it's not that hard to enable this either. And again, this is something that the browser is taking care of. The browser is making these optimizations because images are a huge part of the web today. And this is why I always think that it's risky whenever we try to do things on our own and through some sort of JavaScript framework or library and try to layer these things on, because browsers are going to push these things forward and they're going to continue to improve. And we just have to take advantage of that as it's coming out. And the more we try to overrule what the browsers are already trying to do for us or on our behalf, the less we're going to benefit from these sorts of optimizations. So when I first did the research on this, I was really concerned that this was going to end up being a bunch of micro optimizations that don't really matter. Like, who cares, Thankfully, I think the numbers are a little scary enough to at least strike a little bit of fear and concern into people's hearts. But in case it's not, I also think it matters because we're consistently moving more and more work onto the client. We're using all these client-side frameworks. We're making these sites that are just gigantic, that are doing these incredible new things, taking advantage of all these incredible new technologies that we have. We're making our phone and the browser on the phone do more and more and more. It's Andy and Bill's law, I believe, is what it was originally known as. The idea that as Intel continued to improve their processor speed and power, Bill Gates would just keep taking all that power back and sucking it up inside of Windows, right? We're doing the same thing on the web. Talking to Jeff Veen, who has been around for, I mean, he's worked on, I think he did the Wired site, which was the first major site to use CSS. You know, he's been sort of everywhere. And I asked him, you know, what do you see in terms of, like, if you were looking at the web and how it's changed over time? And one of the things that he said that stuck with me is he's like, you know, I've noticed as bandwidth grows and as processing power grows and browsers get better, we just keep finding new ways to fill it all up. And we keep finding new ways to make that device work harder and harder. So anytime we can do something like this to reduce that memory footprint, to reduce the overhead on the CPU, it's absolutely worth it. Because images are a big deal. It's not just the network, it's the memory, it's the battery, it's the life of the device, it's the overhead. And thankfully, it's not an overly complicated thing to deal with. We just have to make sure that we resize our images so that they're sized appropriately when they're sent to the browser. As those images get larger, if we're doing a responsive design, have those smaller breakpoints so that we can minimize the memory footprint. Meta viewport is your friend, which hopefully it's your friend beyond just the images stuff, but even when it comes to image decoding, it's your friend. And use 420 subsampling whenever you can. Take advantage of the reduced file size as well as the reduced memory footprint that comes with it. Thank you. Good.
Right, we've got like kind of about 4 minutes for some questions on that one. I hope it all sunk in. It's obviously what I took away from that is I say tomato, he says tomato. Right, so there you go. There you go. But there you go. So has anybody got a question for Tim? No, it's stunned. Stunned, right, too. Right, here we go.
I thought I was getting away.
If so we're using an image CDN, so we can like have as many different image sizes as we want, how many like should we be using with like a picture element? Should we have like 10 images, 20 images?
It depends. It depends, which is a terrible answer because nobody wants to hear it. But it's true. It depends on your site, your design, and how much that image size is varying from screen size to screen size. Like, you know, how much does the display of the image change as you move from viewports from mobile to the medium, I said mobile, from small to medium to large screens? How much variance is there in the size? There's a lot of factors that come into play. You know, you can look at it from a perspective of Jason Grigsby had this fantastic idea years ago to do this sort of file size budget approach to responsive images, where you would have, you know, if you set, you know, at every 20K or every 30K that it increases, you decide that's where you're going to put another breakpoint. Now, I'd suggest that maybe you look at making it a little tighter as it goes larger, depending on that, based on what we just saw from the memory footprint. But that's an interesting way to approach it, at least from that consideration. Basically, you want to maximize your file savings and reduce the memory footprint, but you also want to maintain cacheability. So that's the balance that you have to, you know, you have to be watching out for. Yeah. There's options. You can talk. Yeah.
Any more? There was some hands up. Ilya. We'll let Ilya have one.
Actually, less of a question than just a data point. Out-of-memory errors are very common on low-end devices. Very, very common. And the number one culprit is images.
Oh, really?
Yes. So long scrolling pages with many images, the example that you saw, where the image was getting swapped out, that's also very commonly the reason why pages crash.
See, there we go. So they also crash pages. I'm adding that in.
Hi, thank you for your talk. It was very, very good. I have a question about chroma subsampling. For the last few years, I've been working on heavy optimization of images, and something I found out is that with more aggressive subsampling, you get very poor and awful compression of reds in that channel. Have you had any experiences with automating that kind of compression, so it's depending on major color or something like this?
So, yeah, so how do you deal with it? There's a really fantastic algorithm, and I've heard about it like 20 times this week, and I'm blanking on the name. SSIM, structural similarity or something like that. It's a really interesting approach to this, where you're looking at the perceptual difference of the image. So you can actually compare, as you're compressing it or applying further subsampling, you can compare that version to like the original version and figure out how much of a perceptual difference there is between the two images. So you could apply something like that in terms of a way to try and algorithmically or automatically compare and find out a point where you're getting this level of degradation that's no longer acceptable. So instead of applying like a raw, a specific quality level or specific example of level of subsampling for every single image and just hoping it all turns out right, which is not feasible if you're a large company with lots of images, looking at it with this algorithm in mind lets you at least compare the two and find out something that is going to be not distinguishable in terms of quality from the human eye. So that's one way of dealing with some of the weirdness that can impact based on the differences in images that you're compressing. Does that somewhat answer? Okay. If you come up after, I can send you like links and information about that. It's good stuff. It's super geeky.
Okay. Well, I think I need to call time on questions now. So obviously, if you do have questions for Tim, he's going to be around all evening. So come over and try and fry his brain back. Maybe that's the way to do it. But anyway, so we're now going to have like a kind of 5-minute break. If you want to grab a beer, go to the toilet, whatever, and then we'll come back and get on with Ilya's talk.